All right, in this video we're going to be looking at how to find the zeros of a polynomial and some things that we could do with those zeros. But let's start out by looking at a warm-up, just like we normally do. And so for this one, we're just going to simplify some equations. So because we're going to need to know some basic algebra skills for some of what we're doing. So let's go ahead and why don't you pause the video and work on solving these simple equations. So hopefully this will not be an issue for you. So hit play when you're ready to check to see if you did those correct. All right, so you should have gotten x equals 8 for the first one. For the second one, you should get x equals negative 13/3. So if you didn't get that for the first one or the second one, make sure you go back and double check your work with what I've done here, and then make sure that you know how to get those answers, because you will know how to do, you want to know how to do those processes for what we're going to be working on. All right, so today we're looking at this first example. So here they're asking for the zeros of this polynomial, and then we're going to graph the function. Now we've already done things with finding zeros. So remember, to find those zeros, we would just set each of those factors equal to 0 and solve them. Now you don't want to forget about the x that's in front there, so I'm just going to highlight that. You don't want to forget about that x. We would also set that equal to 0. So one of the zeros would just be 0. So we would have 3 x-intercepts, or 3 zeros, at 0, positive 4, and negative 3. So what we're going to do is, if we're going to graph this function, that would be your first step. We would graph those on our x-axis. Those would be our x-intercepts. Now what we want to do is we want to figure out what is the rest of that graph going to look like. And so what we're going to do is we're going to set, we're going to create it where we can create a table where we have in each column, we're going to have one of those factors. So x minus 4, x plus 3. So we could have 4 different intervals. We could have an interval from negative infinity to negative 3. We would have an interval from negative 3 to 0. We would have another interval from 0 to 4, and another interval from 4 to infinity. And so what we want to do is we want to figure out if we just so if we have a number that's smaller than negative 3. Okay, so let's just go through that table. So if we were to pick a number smaller than negative 3 and put it in there for x, well, that's going to be a negative number. If we were to put a number between negative 3 and 0, okay, if I were to put negative 1, negative 2, any number in between 0 and negative 3 and 0 is going to result in a negative answer. Now if I put a number between 0 and 4 in there for x, I would end up with a positive answer. And if I were to obviously put a number bigger than 4 in there for x, I'd also end up with a positive answer. Okay, now let's look at the factor for x minus 4. So using the interval between, for negative infinity to negative 3. Let's say if I put negative 2 in there. Negative 2 minus 4 is a negative number, so I'd get a negative number in there. If I were to pick a number between negative 3 and 0, so let's say if I put negative 4, let's do negative 1 or negative 2. If I put those in there, I would also get a negative number for my answer. Now if I pick a number between 0 and 4, like if I put 1 in there for x, or 2 in there for x, or 3 in there for x, all of those would end up being a negative number. Now notice 4 is not included. So if you're wondering, well, what if we did 4? It's got to be a number between 0 and 4, but 4 is not included in that set, because otherwise it'd be 0. Now if we pick a number bigger than 4, so if I pick 5, 5 minus 4 would be 1, so that would give me a positive answer. So again, we're recording the signs, and you're going to see what we're going to do with these signs in a second. Okay, so now let's go to the factor for x plus 3. So for x plus 3, if we pick a number in that interval between negative infinity and negative 3, well, like let's say if we put negative 4 in there, negative 4 plus 3 would be negative 1, so that's going to be a negative number. If I pick a number between negative 3 and 0, like negative 1, negative 1 plus 3 would be positive 2, so that's going to be a positive number. If I pick a number between 0 and 4 and put that in there for x, that would be a positive number. If I pick a number bigger than 4, that'd be a number, that'd be a positive answer as well. So then what we're going to do is we're going to take, so now we've got all of those different values, what it's going to be in different intervals. Now we're going to multiply those together. So if we multiply them together, a negative times a negative would be a positive, but a positive times a negative would be a negative. If we were to take a negative times a negative, that would be a positive, but a positive times a positive would stay positive. If I were to multiply a positive times a negative, if I were to multiply positive times a negative, that would be a negative, times a positive would be a negative. And if I were to multiply a positive times a positive, multiply that by another positive, obviously we're going to get a positive for our answer. So that's going to help us. So this column here, as far as what the products are those, that tells me that in that interval from negative infinity to negative 3, my graph would be negative. My graph would be below the x-axis. From the interval from negative 3 to 0, my graph is going to be positive. And from 0 to 4, my graph is going to be negative, so it's going to be below the line. And from 4 to infinity, it's going to be positive, so it's going to be to the right side of the line. So then we can sketch a graph of what it might look like. So now we can throw our y-axis up there. And so again, we're just going to use those intervals, what we just found and what we just described, to sketch a graph. The graph doesn't have to be exactly the way it would look. We're just sketching what the shape of the graph would be. All right, so this one is not in factored form, so we're going to have to review how to factor. So let's look at how we would factor this down. So the first thing we always look for is there a greatest common factor? And I see that all of these have an x, but they're also all divisible by 4. So I want to factor out a 4x. Whoops. So I want to factor out a 4x. Now when I do that, I would have x squared plus 1x minus 6. So we want to figure out how we would factor down this x squared plus x minus 6. Now remember what we learned about with quadratics. It's been a while, but for this one, since our a value is 1, we can use a little trick of just looking for two numbers that multiply together to be negative 6, that add together to be 1. And those two numbers, so if my x is in here, those two numbers, since it's got to multiply together to be a negative 6, but add together to be a positive 1, means that the bigger number has to be positive. And so it would be x plus 3 and x minus 2, because 3 times negative 2 would be negative 6, and 3 plus negative 2 would be 1. So now we have it in factored form. So now we're going to use the zeros to sketch a graph. So the zeros here would be at 0, because I'm going to set each of those equal to 0 and solve it. So I'd have a 0 at 0, because if I set 4x equal to 0, I would get 0 as my answer. And then I would get, for x plus 3, if I set that equal to 0, I'd get negative 3 and positive 2. So my graph so far would look something like this. So we would have an x-intercept at 0, an x-intercept at negative 3, and an x-intercept at 2. Now, we could do a couple of other things. We know some things. We don't always have to use that table. So I'm going to show you a different way that we could do this using what we've learned earlier in this chapter. Remember that this original polynomial now, we can use that little trick of the end behavior to help me sketch the graph here. So since my leading coefficient there is positive, means that the graph, the right side of the graph is going up. Remember doing this from earlier. Since the degree here is 3, and that's an odd degree, means that they're going to go in opposite directions. So the left side of the graph is going to go down. So that means the left side of the graph is going to go down, the right side of the graph is going to go up. So we're just going to sketch a line that's going to do just that. Whoops. Try that a little better. Here we go. So that's all we have to do. Okay, let's look at the next one. So we'll do both of these triads together. Normally I'd have you do one of them, but I think this is tricky enough that in reviewing enough concepts that we should probably do these together. If you want to pause it and try this next one on your own, you can. But otherwise, let's see how we could do this one together. Because this is really reviewing a lot of what we've learned in this chapter. So for this one, this is a difference of squares. Remember doing that a couple sections ago. So this would be the same as x squared being squared minus 9 squared being squared. So this is a difference of two squared. So we would have x squared plus 9 times x squared minus 9. Now if we wanted to factor this completely, x squared plus 9 cannot be factored down anymore. But x squared minus 9, guess what? That's still a difference of two squares. How do I know that? Well, I could square x and get x squared. I could square 3 and get 9. So this would be the same as x plus 3 times x minus 3. Now, when I go to do this one, draw my axes here. So my x-intercepts, now if I set x squared plus 9 equal to 0, if I look for those zeros, we're going to get imaginary numbers. Okay, so those are going to be what we call complex zeros. Okay, so those we're not going to use right now. But the x plus 3 and x minus 3, those would be actual x-intercepts. So I'm going to plot those. So I would have an x-intercept at negative 3. So I put one at negative 3 and another one at positive 3. And it's the fact that a is, or the leading coefficient there is positive, means that the right side of the graph is going to go, remember we're going to have two sides of the graph, so since a is, or the leading coefficient is positive, the right side of the graph is going to go up, and since the degree is an even, they're both going to go the same direction. So my graph would look something like this. So that's how we could sketch a graph of what those two would look like. And then you don't have to worry about creating one of those tables like they did in the previous problem. All right, let's look at how multiple zeros can affect a graph. So here we have x minus 1 to the first power times x plus 2. So we don't have any multiples. We have just one factor at x minus 1. We have one factor at x plus 2. And if you notice, this other one, we have x minus 1 squared times x plus 2. So they have the same x-intercepts. But notice the first one there, the x minus 1 squared, changes the shape of the graph. Because that means that at that point, we have technically two zeros. Because if we wanted to write this out even further, we would say x minus 1 times x minus 1 times x plus 2 would be the factored form. And so we'd have two zeros in the same spot where x is 1. So the impact of that is it bounces off, it reflects, or it has a turning point at that 0 where x is 1. We'll look at this one here. So this one doesn't matter that we can't see the bottom of it because my video is blocking part of that, but all we care about is the x-intercepts. So this one has x minus 1 cubed and x plus 2. So notice a common thing here. All of these have the same factors, x minus 1 and x plus 2. But for this one, x minus 1 has an odd number of zeros. So we have x minus 1, x minus 1, x minus 1. We'd have three of them. And that x minus 1, it goes through that point. It looks weird, but it goes through that point. And at x plus 2, we would have another 0 at x equals negative 2. So we'd have a 0 at negative 2, a 0 at a positive 1, and it would go through that point. So let's summarize what we're seeing here. Actually, before that, let's look at these other ones. So here we would have x minus 1 to the fourth power. So again, all of these are x minus 1s and x plus 2s. Okay, so you have x minus 1 to the fourth power. It bounces or reflexes off that point. X minus 1 to the fifth power. It goes through that point. X minus 1 to the sixth power. It bounces off that point. So here's what we're getting at. So this is really important. So you don't have to worry about writing down all of these graphs in your notes. What you can write down in your notes is this key point here. Oops, let's not use red. When the multiplicity of a 0 is odd, the function passes through the x-axis. So let's look at, let's just go back a couple of times here. So if we go back to the previous ones, here when we had an odd, so this would also be 1, it would go through those 2 points. Here we have an odd exponent, here we have an odd exponent, and it went through those points. And then like we said here, we have an odd exponents, so we have odd multiplicities. It goes through those points. Well, what does it mean then when the x-intercept or the 0 is even? Then the graph has a turning point on the x-axis, or it reflexes, or it bounces off, however you want to refer to it or remember it, but it has a turning point at that 0. Okay, so here when it was even, it turned at that point. Here where it's even, it turns at that point. And you could go back to the previous slides and see those. So that's the key there. When we have a multiplicity is just referring to an exponent for a factor. When we have a multiplicity that's odd, the graph is going to go through that 0. When we have a multiplicity that's even, the graph is going to have a turning point at that 0. So let's look at how we can apply that to these problems. So here it says describe the behavior of the graph of the function at each of its zeros. And so here we have f of x equals x times x plus 4 times x minus 1 to the fourth power. So we know that that means that the graph is going to cross the x-axis at 0 and negative 4. Okay, but at this one, since that 0 has a multiplicity, or that factor has a multiplicity of 4, it's going to have a turning point where x is 1. Okay, now in this example, we have x squared plus 9, we have x minus 1 to the fifth power, and x plus 2 to the second power. Now the x squared plus 9, if I set that equal to 0, we get, again, imaginary numbers, because x squared plus 9 would equal x. If I set that equal to 0, we'd get x squared equals negative 9. So we'd be dealing with the square root of negative 9, which is going to be an imaginary number. So we don't worry about that right now. Okay, but the x minus 1 to the fifth power and x plus 2 squared, those are going to have x-intercepts. And since the x minus 1 to the fifth power, so that's got a multiplicity that's odd, that means the line is going to go through where x is 5. I'm sorry, where x is 1 rather. Sorry, where x is 1. It's going to go through that point. For x plus 2 squared, since that multiplicity is even, that means it's going to have a turning point where x is negative 2. Okay. Just summarizing what we just talked about. All right. So now we're going to learn how to find the other complex zeros. Okay, so we're going to learn how to find all of the x-intercepts, including the complex zeros. So just to be clear, the real zeros are the ones that actually pass through the x-axis. So for this one, we can see that the real zero here would be, 2. Okay, so we know that across the x-axis at 2, so we know the real zero is going to be at 2. So if you wanted to, you could put 2 into the function. So they give you the function there, x cubed plus x squared minus 3 times x minus 6. If you put 2 in there, sure enough, you get 0 as your answer. So we know that 2 is a 0. Now, we can use synthetic division to factor this down. Because remember, if we use synthetic division, what's left over is going to be the other factor. So when we do that, you get x squared plus 3x plus 3 would be the other factor. So we have x minus 2 times x squared plus 3x plus 3. Now from that x squared plus 3x plus 3, we're going to use the quadratic formula to find the remaining zeros. Okay, so we had, whoops, let me get my pen here. So we had x squared plus 3x plus 3 was the other factor. So we're going to use the quadratic formula on that. So remember the quadratic formula, we do the opposite of b. So we do the opposite of 3 is negative 3. Plus or minus the square root of b squared, or 3 squared, which would be 9. Minus 4 times a, which is 1, times c, which is 3. All of that would be under the radical, the square root symbol. And we divide that by 2 times 1, or just 2. So when we simplify that, underneath the radical there, so let me actually go back a step. The discriminant, remember we learned about the discriminant last chapter? The discriminant is just the piece under the radical. 3 squared is 9. Then we'd have 4 times 1 times 3, which would be 12. So we'd have 9 minus 12. And 9 minus 12 would be negative 3. So we would have square root of negative 3, which simplifies to be I square root of 3. Okay, so that's what we're going to look at next. That's what they did next. So we'd have negative, so if we broke that apart, we'd have negative 3 over 2 plus or minus the square root of 3 over 2, or the I square root of 3 over 2, however you want to write it. Those would be your other two zeros. So the zeros, all of the zeros for this function would be 2, that's your real zero, that's your x-intercept, but the other zeros would be negative 3 halves plus square root of 3 over 2i, and the other one would be negative 3 halves minus square root of 3 over 2i. So again, we're combining a lot of things that we've learned about in previous chapters. Okay, so we're going to try this one. You could try this one on your own. So here we have this function, and we can see that one of the zeros would be at positive 3. Okay, so I want you to use synthetic division. So remember what we would do next. So we know one of the zeros is 3. So to find the other zeros, we're going to use synthetic division first to get this in factored form. So I'll just help you get this set up. So we'd have 2 -8, 9, and -9. So I want you to use synthetic division to figure out what the other factored piece would be. Whoops, again, didn't mean to do red here. So we want to figure out what the other factor would be so we could use the quadratic formula on that other factor. So why don't you pause the video and hit play when you're ready to check to see if you've done this one correctly. All right, so let's see how you did. So what you should have done here is you should have found, again, using synthetic division, you should have found that 2x squared minus 2x plus 3 would be your other factor. Okay, so x minus 3 times 2x squared minus 2x plus 3 would give you the original equation. So we found that other factor to be this. So we're going to use a quadratic formula on that piece. So we would do the opposite of b, so that'd be positive 2 plus or minus the square root of b squared, so I just wrote that down as 4, minus 4 times a, which is 2, times c, which is 3. All divided by 2a, which would be 2 times 2 would be 4. So under the radical, the discriminant, we would get -8. And so you just need to know how to simplify that. So we'd factor out an I. So we'd have I squared of 8. Square root of 8 simplifies to be 2 square root of 2. So we'd have 2i square root of 2. So square root of -8 simplifies to be 2i times the square root of 2. So now we're going to simplify that. You might recognize that it's all divisible by 2, or you could break it up into 2 fractions. Either way, you end up getting 1/2 plus or minus I square root of 2 over 2, or you could say square root of 2 over 2i, same thing. But those would be your 3 zeros. So our real zero would be 3. Our non-real zeros would be 1/2 plus or minus square root of 2 over 2i. Now, I want to do this one. I want to show you how we could do one more problem. So here, if we had x to the 4th minus 3x squared minus 4. Okay, so we're going to look at this one. Because for this one, we have 2 zeros. So I want you to see what happens if you have 2 zeros. It doesn't matter which one you start out with, but we're going to start using synthetic division to come up with one of the other factors. And so when we use synthetic division, we get this piece here. So I'm just going to put in our x's now. So we'd have x squared, and x cubed. Well, we have this other, so we can use that to factor it down. Okay, so one of the factors is x minus 2. Another factor is going to be x plus 2. Okay, so we're going to figure out then what is the other piece. And so what we're going to do is we're going to take that, what we just found here, to be those coefficients, and we're going to do this all over again now with the other one that we didn't use. So I didn't use -2, so I'm going to do that one next. So I would put -2 outside of there and use synthetic division when we're using -2 as our 0. And now we get 1, 0, 1, meaning that we'd have x squared plus 1 as our other piece. Now, I could use the quadratic formula if I wanted to, but why would I? I mean, there's a lot of tools that we could use. I only have one variable, so I could just solve for x squared. So if I have x squared plus 1, if I set that equal to 0 and solve it, I get x squared equals -1. Take the square root of both sides. So I'd get x equals plus or minus the square root of -1, which is the same as x equals plus or minus I. So my zeros would be the 2 real zeros, the ones that I can see, the 2 and the -2. But then my non-real zeros would be at I and -I. Okay, so I wanted you to see how we could simplify that if we had 2 x-intercepts, because that's going to be the only tricky one. So if there's 2 x-intercepts, use synthetic division twice and just keep breaking it down until we get something that we can solve simpler, maybe with the quadratic formula. Or in this case, we could skip the quadratic formula and just solve for x. But that is how we do that last example.